All right, we got a lot to do in this video, so we're going to go really fast. So feel free to stop the video and rewind it if you need to. Check my work to make sure that everything is on the level. Here we're going to talk about conservative and non-conservative forces. With so-called conservative forces, it's easy to get useful energy back out of the system. With non-conservative forces, it is difficult. When we displace an object from one point to another, the work done by a conservative force is independent of the path taken. It doesn't matter how you get between point A and point B. The amount of work done by the conservative force will be equal, no matter what path you take. Let's try and show this with an example. Let's explain what's happening here. You can see the picture. We have a 4-kilogram mass right here at the origin, and we're looking at it from the side. So gravity is acting down, and we're going to move this mass up to this location here, which is at the point 3, 4, 3 meters, 4 meters. We're going to take two paths to get there. We're going to take the red path. We're going to take the green path. At the top of the screen, the work done by gravity is m times g times the change in height. The mass is 4, g is 10. And so for each of the three paths, the red paths, I've calculated the work. There is 0 work done here because the change in height is 0. Then gravity does negative work when we're lifting something, and then 0 there. So those are the three amounts of work done by gravity when we take the red path. If we take the green path, where we lift this mass up higher than it's going to end up, then we slide it over, then we drop it down. Again, using the same equation that's at the top of the screen, we're raising something up first, so we're doing negative work. Then we're sliding it over, so we do 0. Then we're dropping it down, and gravity does positive work. Now, how does this shake out? If you add up the red works and you add up the green, you get the same value. So what we said just a second ago was that the work done by a conservative force is independent of the path, and you can see that with gravity. What about with friction? Here we're taking the same essential diagram, except now we have a top view of a mass being slid along the floor. I've left all the other dimensions the same, but now we have a bird's eye view looking down, and we're going to slide this mass along the red path, and then we're going to slide it on the green path, and we're going to figure out the work done by friction. At the top of the screen, work is force times distance, so the work done by friction is the friction force times the distance, and we're told in the problem that we're going to assume the friction force is always 4 newtons. So if you take the red path, negative 16 joules, negative 16, negative 4, friction always does negative work because the friction force always points opposite the displacement. If you take the green path, and perhaps I should have written these numbers in green, you get negative 24 there, negative 12, negative 8. When you sum up the green values and you sum up the reds, you do not get the same number. That would indicate that friction is a non-conservative force. And so that's what we're going to say here. Label is conservative or non-conservative. Gravity is conservative. Friction is non-conservative. Two other conservative forces that we'll meet in this series of videos are the elastic force is also a conservative force. And then if we talk about electricity and magnetism in another unit, electrostatic force is also conservative. All right, here's our last important point for paths. The work done by a conservative force over a closed path is 0. A closed path means that the starting and stopping points are the same. Again, we're going through this quickly, so you can feel free to rewind the video and look at the diagram again if you want. But if we start at the origin and we take segment alpha, then beta, then gamma, those were the red ones, and then we take these green ones. If we end up back at the origin, if we go all the way around the horn, this is the amount of work done by gravity in each case. Look at that, it adds up to 0. For friction, if you go all the way around the horn, starting at the origin and ending at the origin, each segment along the way has a negative work, negative 80 joules. the point that's at the top of the screen, the work done by a conservative force over a closed path, if you start and stop at the same point, it should be 0. It is for gravity. It is not for friction. All right, last idea for this video. The work done by a conservative force is equal to the change in potential energy. If we look at this picture here, we have a 4 kilogram mass, and it's on the floor or it's 2 meters up. If we raise this up, gravity does negative work. In this case, figure out the numbers, negative 80 joules. Well, isn't it true that the gravitational potential energy is going to increase when you raise something up? So look at the equation that's now at the top of the screen. You can see that the sign of the work and the sign of the change in gravitational potential energy should be opposite, and they are. See, negative, and that's increases. And those are opposite signs. Increases is a positive change. Similarly, if you drop this mass down, gravity is going to do positive work. And what's going to happen to the gravitational potential energy? It's going to decrease. One more time, the sign of the work and the sign of the change in potential energy should be opposite, as they are in these funny shaped things that I've bubbled in and shown in that equation there at the top of the page.